Hello, my name is Kavide, and I'm going to present our paper, Cursor-Based Robot Telemanipulation through 2D to SE2 Interfaces. This paper is based on work I conducted during my internship at the Paul G. Allen School of Computer Science and Engineering at the University of Washington in collaboration with Maru Kavera, Kavita Krishnaswamy, Tapo Bhuchatterjee, and Maya Kakmak. The goal of our research is to enable direct control of mobile manipulators through a simple cursor interface. Here is an example of an existing interface that does exactly that. By moving around and physically interacting with the environment, mobile manipulators like the PR2 can perform a wide range of tasks to assist humans with the daily activities of living. However, doing so autonomously is extremely challenging given the lack of structure and vast amount of variability in everyday human environments. Instead, a human-in-the-loop controls of such robots is much more feasible and can enable many use cases of mobile manipulators in the near term. Our research focuses on cursor manipulation because of its wide availability and accessibility with assistive devices. Although there is a large body of prior work on robotic teleoperation, there are very few comparative studies that investigate how basic interface design choices impact the efficiency of the interface. Efficiency is critical for teleop interfaces to be practical. Current state-of-the-art cursor-based interfaces can take several minutes to perform manipulation tasks that an able-bodied person can perform in seconds. So there's a lot of room for improvement in efficiency, and we hope that better understanding the impact of design choices is an important step in making progress. While we hope to make teleop interfaces accessible by focusing on cursor input, we are also interested in how the interface design can further improve accessibility. One of the key challenges is controlling many degrees of freedom with limited input. We are trying to control the robot's end effector pose, which is 6-dimensional as we need to specify both its position and orientation, with the cursor, which only specifies 2 dimensions. That is, its XY position on the screen, and is often augmented with a click, for instance using a mouse button, which can either be considered as a binary state or an event. In order to get to the core of how user interfaces allow going from a lower dimensional input to a higher dimensional output, we start with the simplest version of this problem that is still fundamental to the control of robots. That is, going from 2-dimensional cursor input to a 3-dimensional SE2 configuration, which corresponds to a position and an orientation in a 2-dimensional space. For example, the pose of a differential drive mobile robot navigating on a surface is specified in SE2 space. So, this term from our paper title, 2D to SE2 interfaces, basically stands for user interfaces for specifying position and rotation in 2D through a cursor. Here is an example of such an interface where the 3 dimensions in SE2 are manipulated one at a time, and different regions around the object, which are visually indicated with arrows in a ring, act like buttons that activate movements in one of the dimensions. When the button is pressed, the cursor position is then applied as a change in the corresponding dimension. So, that's one example of a 2D to SE2 interface. In our work, we explored 5 different interfaces that were inspired from previous work. I'm going to describe these 5 interfaces in a bit more detail and talk about a comparative user study to evaluate these interfaces. And later, I'm going to talk about how we can use these interfaces to control a robot manipulator. Our first interface is what we call the fixed interface, because it has control buttons that are fixed on screen rather than ones that move with the object being manipulated. So it has a total of 6 different buttons, corresponding to 2 opposite directions in each of the 3 dimensions of SE2 that can be manipulated by the user. The second interface is the one I showed earlier as an example, and we call this one arrow ring. The third interface, circle ring, has 2 elements, a ring and a circle that move with the object being manipulated. The circle is used to move the object in X and Y simultaneously, and the ring rotates the object similar to the arrow ring interface. The fourth interface, target anchor, has no control buttons. Clicking on the screen moves the object to the click location, and the follow-up click rotates the object to face the cursor. The last interface, target ring, is similar to target anchor. Clicking on the screen sets the location of the object, and clicking on the ring sets its rotation. So, these are the 5 different 2D to SE2 interfaces we explore. Notice how the first 3 interfaces use the 2D cursor position to specify the movement of the object relative to its current position, whereas the latter 2 interfaces specify the target independent of the object's current position. In our paper, we describe how each of these interfaces can be represented as a finite state machine, where user-triggered events, such as pressing or releasing a mouse button, result in a state change where each state behaves differently. We also note how those user events that trigger state transitions can be chosen differently to create different versions of the interface. The interfaces I have shown so far use the mouse press and mouse release events for state transitions. In this work, we also created a version of some interfaces that use the full mouse click as a single trigger event. We did this as a way to increase accessibility based on recommendations from prior work that demonstrate challenges associated with dragging actions. Let's play that again. As you can see, the user clicks once to start moving the object, and then clicks again to stop it, and then another click sequence to start and stop rotating. For the target ring interface, it doesn't make sense to have an interface just based on press or release, so we have in total 9 different interfaces. Our first study was a systematic comparison of these 9 different interfaces. The goal of the study was to understand how the different interface choices impact the efficiency of the interface at a basic level. To measure efficiency of the interface, we use a simple metric, task completion time across different tasks. The task is simply to move an abstract SE2 object from a start pose to a target pose using the interface. We asked participants to perform 36 different variations of this task, which I'll explain next, and we took the average across those tasks. A task starts when the user clicks a button that says "I'm ready," and ends when the target is reached, so people could take time between tasks to rest. The task of moving an SE2 object to a target can be made harder or easier in different ways. For example, a target that is further away and oriented in the opposite direction will take more time to reach. Similarly, as we know from Fitts' law, reaching a smaller target is harder than reaching a larger one. We wanted to cover the range of task difficulties in our study and characterize how efficiency changes across those task variations. To that end, we vary the task in terms of both the distance and size of the target. The distance is varied by keeping the start pose of the object at the center of the screen and sampling target poses within increasing radius at random directions. The target rotation is similarly sampled between 0 and 180 degrees from the initial orientation of the object. The target size is varied by changing the threshold for position and rotation distance to an exact SE2 target pose, within which the object is considered to be at the target. We visually represent such flexible targets with larger size, with a gray shadow area around the exact target pose. The circle indicates the position threshold, and the arc indicates the rotation threshold. So, the 36 task variations have randomized position, size, and rotation, and every task looks a bit different. Here is an overview of our study procedure. For each participant, we randomly select one out of the 9 interfaces. So we have between participant study design, where a participant only interacts with one interface. The participant first watches a short tutorial video that introduces them to the interface and the task. They then practice using the interface until they successfully complete at least 5 tasks. Then they move on to the main part of the study, where they complete the 36 task variations at their own pace. Afterwards, they are asked to respond to a questionnaire with some standard and custom Likert skill questions, as well as open-ended questions about the interface. We recruited a total of 216 participants. That is 24 participants per each of the 9 conditions. Our participants were recruited over Amazon Mechanical Turk and were compensated with $2. They took an average of 34 minutes to complete the study. Here is a selection of findings from this study. In this graph, we show a box plot of the task completion times across the 9 different interfaces. The vertical white line indicates the mean, and the error bars show quartiles. We performed a statistical comparison using a factorial model to compare the interfaces. The stars indicate statistically significant differences. Our first observation is that the 2 target-based interfaces were the most efficient among the different types of interfaces, saving up to 10 seconds on average when compared to the less efficient interfaces. This difference was statistically significant, and there was no difference between the target ring and target anchor interfaces. This finding is expected, since the movement-based interfaces require tracing a path to the target and therefore require more time. In this graph, we present a scatter plot of task completion time versus target distance and target size, where larger target distance and smaller size corresponds to harder tasks. We can see, for instance, how the fixed interface gets slower by about 10 seconds on average as the task becomes more difficult. Similarly, we observe that the efficiency of all movement-based interfaces are impacted by target distance, whereas the target size does not have the expected effect for the arrow ring and circle ring interfaces. Lastly, we see that the target-based interfaces are not at all impacted by task difficulty, which contributes to their overall efficiency. Among the 3 movement-based interfaces, we see that efficiency increases when we take better advantage of the continuous cursor movement. The fixed interface, which completely disregards the cursor pose information, is the least efficient interface, while the circle ring interface, which maps cursor pose directly to the object pose during positioning, is the most efficient among the 3. The next step in our work was to develop the interfaces for controlling robot manipulators, using these different ways of controlling SE2. In particular, we focus on direct control of the end effector of a standard 6 or 7 degree of freedom robot arm, which corresponds to control in SE3. That is three-dimensional position x, y, and z, and three-dimensional rotation around the different axes. We achieve that through an interface that displays the robot manipulator from three orthogonal views and allows the control of an end effector on a plane that is parallel to each of those views. Here is an example that uses the arrow ring controller. The user chooses the view for controlling the robot by clicking on it and using the control within that view exactly the same way as in the earlier abstract examples. They can continue to observe the robot in all of the views. The video shows an example of how the user can combine two views to control the robot's position in 3D. Now let's see how all the other control interfaces look as part of the manipulator control interface. This is the fixed interface. Here is the circle ring interface. Here is the target anchor interface. And lastly, here is the target ring interface. Our second study is a comparison of these manipulator control interfaces. The study design and procedure were very similar to the first study. This time we only had 5 conditions. Rather than having both versions of each type of interface, we only provided press-release-based control or click-based control, depending on which version was most efficient from the first study. The task is simply to move the robot's end effector to a pose where it can grasp the target object. The study includes 5 tasks with increasing difficulty, involving 2 different objects placed at different poses. We again recruited participants over Amazon Mechanical Turk. This time, we had 12 participants per condition, with a total of 60 across the 5 conditions. Here is a selection of findings from our second study. First, we observed that some of the trends from our first study did not carry over to the second study. For example, the target anchor interface, which was one of the most efficient interfaces in our first study, was one of the least efficient interfaces in this study. This was likely because the ghost end effector visualization, which allows the user to set the orientation once the position has been set, was less intuitive in 3D. Participants commented that the control was too sensitive and difficult to orient as intended. Another difference from the first study was that there was no significant difference between the most efficient movement-based interface, which is circle ring, and the most efficient target-based interface, which is target ring. They had very similar efficiency. The trend among the 3 movement-based interfaces, on the other hand, was very similar to that observed in the first study. The subjective ratings of the interfaces also reflected the issues associated with the target anchor interface in SE3 control, which had the highest mental demand, effort, and frustration level ratings. Users also indicated this interface was significantly less intuitive, more difficult to learn, error-prone, and harder to recover from errors as compared to the other interfaces. Those are some of the key findings from our 2 studies, which begin to answer this important research question we posed earlier. If we set out to design the most efficient interface possible, we have a good idea of what to do. What we haven't discussed so far is how these design choices impact the accessibility of the interface. As mentioned before, accessibility of the interface for people with motor limitations is critical for many use cases of mobile manipulators aimed at increasing independence. Although we did not formally evaluate our interfaces with this target population yet, our research team included 1 person from this population, and we performed a heuristic qualitative assessment of these interfaces in terms of accessibility based on issues raised in prior work. We considered 4 heuristics. First, interfaces that require precise cursor positioning are less accessible. In our studies, the fixed interface was the most accessible in this regard, as the position of the cursor was not used as part of a continuous mapping function. It just needed to be within the region of the correct button. Second, interfaces that require holding a button for an extended duration and dragging the cursor while holding the button are less accessible. This motivated the inclusion of click-based interfaces in addition to press-release ones in our study. Third, interfaces that have a smaller number of discrete actions at any given time are more accessible. This heuristic does not apply to the comparison of the different interfaces, but it was a guiding principle when designing the orthogonal view interface for SE3 control. Lastly, larger buttons arranged close by are more accessible per Fitts law, which again does not allow a comparison, but guided how we designed the fixed interface. Overall, we can see that the fixed interface, especially with click-based transitions, is the most accessible interface. Even though it is among the least efficient interfaces, its user experience based on subjective ratings from participants is comparable to more efficient interfaces. If the user does not have any issue with precise cursor positioning, then the circle ring and target ring interfaces are the best choices for maximizing efficiency. Our results clearly point toward the need for customization to the particular user to attain the highest efficiency while being accessible. We also hope to evaluate our work on real mobile manipulators with a target population. We invite you to try out the different interfaces presented in this work yourself at our GitHub repository. Thank you for listening, and we hope you check out our paper for more details and get in touch with any questions or comments.